Okay, so we're looking at tracker for the Magnus glider, and what I've done is I've just tracked the motion of the center of mass, and then I've tracked a point on the edge of the glider, so that you can see both the motion of the glider itself and the rotation of the glider. And the way that I did it was, just zoom in here, was in order to find a point to track here, I noted that if I go to a later frame here, I noted that the dark point on the rim was perpendicular to the black line in the center. And once I knew that, then even when the dark point on the rim was not visible, as it isn't in some of these frames, so there, now it's disappeared, I could still find where it was by just going perpendicularly out from the black line. So I was always perpendicular to the black line, and always on the rim of the glider. Okay, so that was how I tracked the point, and then you can extract all kinds of cool data from this. So the first thing is y and x. So to do this, I had some axes. I also put in a tape measure, assuming that the width of this was about 8 centimeters. I have no idea if that's what the width actually was, so you'll need to check that. And the first thing is to put in some axes, and I put my axes exactly at the launch point. And then the first bit of data that I can extract is the vertical displacement data, which is y. So that's here and here. So I'll just select all of that data. I'll select t first and copy that. I also put it to the starting point to where I first started tracking the rotation. So I selected a starting point that would allow me to really see the rotation. Okay, so I'll put t into my first column here, and that's time for mass A. The reason why it says mass A there is that mass B is what I call the point on the rim. Okay, so then I can select y here by double-clicking on the column, and I'll put that into my y column here. So that's my vertical displacement. Before I do anything else, I should probably name these. And that's, I'll call that y, and the units are in meters. And then my next column is going to be my x displacement. And I want to make a little change here before I do the x displacement, because I want it to be positive. So I'm going to spin my axes around like this, and then just make sure it's horizontal by making this exactly 180 degrees. Okay, so now that looks kind of horizontal. In fact, what I want to do really is line it up so it's parallel with the track, which was horizontal, which is pretty good. The camera was pretty good. Okay, so now my x displacement here, I can copy, and I'll do data, new manual column, and I'll call this horizontal displacement x, and that's in meters. Done, and I'll paste that in there. Okay, that's the linear motion, and I'm not going to remove any of these columns just yet, these rows just yet, because I want to put all of my data in before I do that. Okay, so the next thing that I want to do is I want to get the rotational motion of this bit here. So then I'll go to the coordinate system, change my reference frame to mass A, which takes a moment. So now the axes, if I go forward frame by frame, the axes move along with the red point, which means that I can use the blue point to measure the rotation of the glider at all points. So the data that I'm interested in now is not x and y. The data that I'm interested in now are theta, the rotation angle, and omega. So now what I'm going to do is for all those times, is copy the rotation angle, This is called angular displacement in degrees. Whoops, I'll just put that here. The usual symbol for angular displacement is omega, and the unit in this case is degrees. Okay, did I copy it? I think I did. Oops, the symbol is not omega. The symbol should be theta. And I'll paste that data in here. Oops, that says mass A. That's not what I'm interested in. So I made a mistake there. Go back here. The one whose angular displacement I'm interested in is mass B. So I'll take all that data and stick that in here. And then I want another manual column. This is going to be the angular velocity. Oh, in fact, I'm not going to get that from the program because the program was really bad at working that out. Now what I can do here is I can look at the vertical displacement. I can look at the horizontal displacement. And I can look at the angular displacement. And the angular displacement seems to be changing at a fairly constant rate, which means that it's not the rate of spin is changing only gradually. Yeah. Okay, so the next little bit that's interesting here is that we can figure out what the velocities are. So to do this, what we need to do is work out the time derivative of the displacements. So the first thing I'll do is you need to change the settings to make this work nicely because we plotted so many points. It says here that the number of points for derivative calculations is 7. That means that it uses 7 points to kind of figure out a rough gradient, and then it works out the derivative. But with only 7 points, it's changing all the time because of our crappy tracking. And so what we need to do is use many, many more points, because this is loads of points. And so if you use 97 points instead of just 7 to do this, then we'll get a better, smoother curve, at least for the derivative. Okay, and then what I'm going to do is go to Data and New Calculated Column. And I'm going to have the vertical velocity. And that's going to be called Vy. And the units for that, or maybe I should call it dy dt, because it's from a derivative. And the units for that are meters per second. And the expression then, if you want to work out what the vertical velocity is, all we need to do is take the derivative of the vertical displacement. Actually, sorry, I should just rename this column. This is not x, this is time. Done. And then now I can put in the calculated column, and this is going to be the vertical velocity, and that's dy dt, and that's going to be in meters per second. And the time derivative of the y displacement is the vertical velocity. So we'll go calculus, derivative, variables, vertical displacement, comma, and we want to get the time derivative, so we'll put time in there. And that gives us a new column, which is the velocity. And then we can go Data, New Calculated Column, and we can get horizontal velocity, dx dt, and the units for that are also meters per second. And the expression is going to be calculus, derivative, variables, horizontal displacement, comma, time. Done. That's the horizontal displacement. And then the other thing we can do, sorry, the horizontal velocity. The other thing we can do is work out what the angular velocity is in degrees per second. So let's do that. Or maybe we can also work out the vertical acceleration. So if we go analyze, data, new calculated column, we can go vertical acceleration, and we can call it AY, and that's going to be units of meters per second superscript squared. So that's going to be the second time derivative of the displacement. So we go calculus, second derivative of vertical displacement with respect to time, done. And then we can also get the horizontal acceleration. AX, the units are meters per second squared again. And that's again going to be the second time derivative of the horizontal displacement, comma, with respect to time, done. Okay, so let's have a look at that data now. So if we check this graph out, we'll get the vertical velocity, and we can see that the vertical velocity kind of starts off being positive and increases, and then as it moves up, it's going to start to decrease, and then at the top it has a zero vertical velocity, and then the vertical velocity starts to decrease, and it's negative, and it stays roughly constant as it heads down, and then the vertical velocity slows down as it approaches the end of its trajectory. Cool, and these wobbles come from the fact that we're using 97 points, so don't worry too much about the wobbles, it's the overall trend that we're worried about. The horizontal velocity looks like this. So initially it starts off moving in the positive direction very rapidly, and then it slows down very quickly, just decelerating here horizontally, and then it remains at a very, very low horizontal velocity for a while, and that's when it's at the top. Then it starts to increase again as it's heading down. Okay, so that seems to match what we've seen. The vertical acceleration, okay, acceleration always ends up looking a bit more crazy, but still we can identify a trend here. So let's have a look. The vertical acceleration, so it starts off with virtually zero acceleration, because I've basically started this when it's left the spring. So it's kind of heading up, it's almost in equilibrium here. And then it has a large negative acceleration when it approaches the top. So that's when it kind of flattens out. And then here it's momentarily in free fall. I'm assuming that's when it's actually at the top. And then its vertical acceleration slows down to zero again as it's heading down at a constant speed. So it's not accelerating. And then it heads into it kind of remains at a constant speed for the duration of the part that I've tracked. Okay, so that's the linear stuff. Now we can do the same for the angular stuff. So another interesting thing to calculate is the angular velocity. So that's how quickly it's spinning. That's how many degrees per second it rotates with. So we'll call the usual symbol for angular velocity is the lowercase letter omega, and it has units of, in this case we're using degrees, so it's degrees per second. And the expression for that is going to be the time derivative of the angular velocity of the blue point that I tracked, which was mass 2, which I called theta here when I exported it. So the function is going to be calculus derivative, and I'm going to be looking for the angular displacement, and I'm going to differentiate that with respect to time. There we go. So now I have an angular velocity here as well. So I can have a look at how the rotation changes. Okay, so there we have it. Let's just zoom out a bit. So I'll make that negative 30,000. And I'll just drag this across. So what happens to the angular velocity, or the number of degrees per second that it spins around? Well, as expected, it gradually slows down during the trajectory. So the spinning gradually gets slower and slower. So here, if we wanted to, we could try to fit a line to some of this data. It looks like at the end something weird's happened because it suddenly droops. And then we go analyze, linear fit, and we can see that the angular velocity decreases at a rate of 4,233 degrees per second. Remember, this is a very, very short time that it spins through all these rotations, so the angular velocity is very large, and therefore the angular acceleration is also quite large, even though it appears to change quite gradually. If we wanted to make it seem more reasonable, what we could do is convert this to a revolutions per second instead. So what we could do is angular velocity RPS. So we call this like something like Greek lowercase omega RPS, and the units for this will be RPS, revolutions per second. And so what do we need to do to convert that? Well, we take the variable angular velocity and we divide that by 360, because 360 is one revolution. Done. So now we can see what the angular velocity looks like in revolutions per second instead, because these large numbers are kind of meaningless. Okay, so it looks like that. It should be exactly the same as the other one, so I'll make it negative 60 so we can get a bit of a better view, and I'll make that 0. So here we can see that the angular velocity in revolutions per second starts off at something like 34 or something, ends up at something like 25. And the reason it's negative is that it's spinning sort of clockwise instead of counterclockwise, which is usually considered the positive direction. Okay, so that's basically how you can use all the data from Tracker to draw all kinds of conclusions. So, for example, if we look at the vertical acceleration, we can see that between times 0 and 0.12 seconds, it's not accelerating at all. And what does that mean? Well, we can look at the horizontal displacement and see what it means. So during the time 0 and here, there's not really any acceleration. It's moving at a roughly constant speed. And then there is an acceleration, which we can see here. There's a big curve in the displacement graph. Let's look at the acceleration graph again. Horizontal acceleration. Oops, that wasn't what we were looking at. Actually, it's the vertical displacement that we're interested in. So the vertical displacement looks like this. It's constant, 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 and then it starts to decelerate here. So the vertical acceleration, let's look at that. Here we go. So it's constant, 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 and then it starts to decelerate, right? So that's the curved bit. In fact, we can just look at these alongside each other. File, how do I get that? I can insert a new insert graph. Here we go. And I'll put that alongside the other one, and I can compare what's going on with the displacement and the acceleration. So here's the vertical displacement, and I'll frame that. So first we have 0 acceleration up until this point, and then we have a negative acceleration. So that's this curvature, this negative curvature here, up until this point. Then it moves at a roughly constant speed, and we can see that here. It moves at a roughly constant speed until the end of the motion, basically. So the places where it's in equilibrium, we'd assume that the magnus force upwards is equal to the weight force. At this place, it looks like it's accelerating at about -10. So it looks like during that part of the motion, this one here, it's in free fall. The magnus effect isn't doing anything. Basically, the glider is just a projectile. And then as it just passes the top of its trajectory, the downwards acceleration starts to decrease. So the magnus effect is slowing down the fall of the glider. Well, either the magnus effect or air resistance is doing that. And then as it falls, it's once again in equilibrium. So as it's moving through the air again, the magnus effect starts to take hold on it once again. And that's interesting from the point of view of the horizontal displacement, because if we look at this, horizontally, it's not moving here. Because it's not moving through the air, we have no magnus effect, so we have a downwards acceleration of -10. This is a eureka moment right here, because this tells us that while the magnus glider is not moving forwards through the air, it's accelerating downwards at -10 meters per second. That's like a wow moment, because it really shows you that for the magnus effect to work, the magnus glider has to be moving horizontally forwards through the air. So once it starts moving horizontally forwards again, we get the magnus effect. And it looks like it's kind of triggered by it falling down. So once it starts its free fall downwards, then it's once again moving through the air, and that causes it to start to move forwards too. So it looks like a kind of complicated thing, but these graphs can really be used to explain it. So analyzing this data is going to give you the whole solution to this problem, I think. So I hope that helps, and ask me about anything that you're unsure of.